Hi everyone, in this video I am continuing this problem of how to find pH of a weak acid strong base titration. This is the second part of the video where we're going to actually start calculating pH. So this is the scenario we were given. A student titrates 30 milliliters of acetic acid, which is a weak acid, with 0.1 m sodium hydroxide, which is a strong base. It takes 23.55 milliliters of this base to reach the equivalence point. And then we are given the Ka of this acid. So first thing I like to do is write out my reaction and list my variables. So a common misconception is people think equivalence point means pH of 7. It doesn't. Equivalence point means the moles of base you added equal the moles of acid there was initially. That's what that means. This equals this initial amount. And so what you should always do starting out these problems are use your data from the equivalence point to get moles. And so that's what we're going to do first. Our sodium hydroxide we knew was 0.1 m. And I'm calling it just OH because the sodium, as we said in the last video, is a spectator ion. You don't need to write sodium. It doesn't do anything. That will equal moles of OH over the volume of the base it took to get to equivalence. So 0.02355 liters. That tells us that my moles of OH that were added, or that were used to get to the equivalence point, that is equal to your moles of acetic acid. So how many moles of acid there were initially? That equals 0.00235. So that's how many moles of base I added to get to the equivalence, and that's how many moles of acid there were total initially. And that is always the first thing you need to do. The second thing you might want to do when you see these problems is look at the Ka. So the Ka for acetic acid is 1.73 times 10 to the negative 5. And go find the pKa. To get the pKa, you just negative log the Ka for that acid. And so if I negative log 1.73 times 10 to the negative 5, I get that the pKa is 4.76. Because during these titrations at the midpoint, which is halfway to equivalence, pH equals pKa. And again, I talked about that in the first video. And I like to write that down. And so what is halfway to equivalence? Well, if equivalence is that many milliliters, just half it. So add 11.78 milliliters. The pH will equal the pKa because that's your midpoint. My pKa is 4.76. So at that point, the pH is 4.76. So as you solve these problems, you can kind of check your work. Because if you're asked to find the pH before the midpoint, it should be less than the pKa. If you're asked to find the pH after the midpoint, it should be greater than the pKa. So that is a helpful number to know. Okay. So the first thing I want to find is, let's find the pH before you add any base. So when it's just acid, right now there's only weak acid. How do you find the pH of a weak acid? It is not just the negative log of the molarity. Because this is a weak acid, it comes to an equilibrium. And so let's write that reaction. What does this do at equilibrium? It goes like this, and some of it will dissociate to form a hydrogen ion and an acetate ion. And so you need to make an ice table. ICE. Now, ice tables are not for moles, they're for molarity. Well, how many moles or how much molarity do I know there was? We already solved that by solving for the moles of base at equivalence. That tells us our moles of acid initially. So that's that number, 0.002355 moles of acid initially. Divide it by, what's the volume of my acid? 30 milliliters, so 0.03 liters. When you divide those, we get that the initial molarity was 0.0785 N for my acid. I'm going to put that here on my ice table. Just start at 0. Change. Your acid gets a negative X. The hydrogen ion and the acetate ion get a plus X. For equilibrium, it is 0.0785 minus X, and these two get to be just X. Okay. E rows always get set equal to a K. This is an acid, so I set it equal to the Ka. So 1.73 times 10 to the negative 5 equals X squared over 0.0785. You're allowed to use the 5% rule for this, so get rid of that X. Okay, and now you just solve for X. So 1.73 times 10 to the negative 5 times that, and then square root it. We get that X equals 0.001165. And again, that's the concentration of my hydrogen ions and the concentration of my acetate ion. And so to get pH, pH is the negative log of your H. So negative log that X. And we get that the pH initially for this is 2.93. So there is the initial pH. It's just an ice table. Next, we're going to solve for the pH at equivalence point. In my next video, we will solve for the pH before the equivalence point when the solution is a buffer. So now we're going to find the pH at equivalence. I know we're kind of skipping around. And so you should know, because this is a weak acid, strong base titration, that the pH is going to be greater than 7 at equivalence. And let's talk about why. So again, this is the reaction that's happening. And at the equivalence, you've added in the base, and we added in 0.02355 moles of this. It neutralized all of the moles of this, and what you're left with is water and conjugate base. Now this is all a 1-to-1 reaction, and so because I added this many moles of base, which again we took from the molarity and the volume, that means I made that many moles of conjugate base. And so I want to rewrite this reaction on my separate sheet of paper. So this is what is happening. All of this is technically gone. All of this is technically gone. And we're only left with water. We don't care how much water is. And this. And the amount, because these are all 1-to-1, the amount of moles of base that I added is for right now moles of conjugate base. And I'm saying that with parentheses because I'll explain in a second. So that's how many moles of this that were technically made, because all of this neutralized all of this. Well, this is a conjugate base. As I said before, you have to understand that something that is weak, a weak acid, will make a conjugate base. You have to know that. And you have to know that conjugate bases, their reaction will go in reverse, versus a strong acid, strong base won't go in reverse. And so when this goes in reverse, let's go ahead and rewrite it. This conjugate base will react with water and be a base. And when it's a base, it takes a hydrogen ion. So it forms OH and an acetic acid molecule. But by forming OH, it has driven the pH up. Because even like 1 drop of hydroxide will shoot up the pH above 7 if it was neutral. And so we need to find pH at equivalence. This is not a strong base, though. It's a weak base, just like that's a weak acid. So it comes to an equilibrium. Anytime you have equilibrium, you make a ice table. So initial, change, equilibrium. When in doubt, make an ice table. Water doesn't go in your ice table. And again, ice tables need to be molarity. So this is my moles of conjugate base, 0.002355 moles. To get molarity, I need to divide it by the total volume. And so let's go back and look. We had 30 milliliters of acid, and we combined it with 23.55 milliliters of base to get to equivalence. So that's what's in the flask right now, volume-wise. 30 plus 23.55 is 53.55, so 0.03. There we go. And that molarity is 0.0439 m. So that's my initial for this. This reaction will come to an equilibrium. So you set up your ice table, you set up your E row. Okay, now where this can be a little bit tricky, and again, it just requires you to remember some things. E's get set equal to a K. Your equilibrium row always equals a K. This is a base. You're expected to know that the opposite of a weak acid is a base. So I cannot set this row equal to a Ka because this is a base. It needs to be set equal to a Kb. Well, how do we get Kb? We know acetic acid's Ka. We wrote it, it was in the problem. The Ka for this was 1.73 times 10 to the negative 5. And there is a formula, Ka times Kb equals Kw. And that works for an acid and its conjugate base. It also works for a base and its conjugate acid. And so the Ka for this, again, was 1.73 times 10 to the negative 5. We need to find Kb. Kw is for water. And so anytime you multiply Ka times Kb, it equals water's equilibrium constant, which is that. And so that gives me that the Kb for this is 5.78 times 10 to the negative 10. And I can set my E row equal to that. X squared over 0.0439. I solve for x. And again, you just need to be careful. X is not H, X is OH. So that times 0.0439. Square root that, and we get it's 5.03, let's say 5.04 times 10 to the, how many zeros is that? 1, 2, 3, 4, 5, times 10 to the negative 6. Now once you have your concentration of OH, you can't find pH yet, you find POH by negative logging your OH. Get POH equals 5.29. pH would then be 14 minus that. And 14 minus 5.29 is 8.71. So that's how you find pH for the equivalence point of a weak acid, a strong base. You pretend that all of this, not pretend, all of this was neutralized. And the amount of moles of base you added to neutralize is how many moles of conjugate base you made. You find the molarity of your conjugate base by dividing it by the total volume. Set it into an ice table to figure out how much OH gets made from the conjugate base. Because all of the OH that you added was neutralized, but that conjugate base works in reverse and makes some OH by itself. So all the stuff you added, gone, but this makes more OH. And again, you have to use the Ka of your acid to get the Kb for this base. Solve for x. X equals OH, and you get POH. I hope this was helpful.